here we are with exercise 9 in chapter 6. Now, earlier in the chapter, I explained a little algorithm, a simple algorithm for determining whether a vector is in the column space of a matrix. And it's a pretty straightforward algorithm. Basically, we take the rank of the matrix. So you compute the rank of the matrix, and then you augment the matrix with the vector in question. And then you compute the rank of that augmented matrix. And if the two matrices have the same rank, then the vector is in the column space of the matrix. And if the two matrices have different ranks, then the vector is not in the column space of the matrix. Okay, I explained the reasoning behind that earlier in the chapter. And now we are going to empirically confirm this. So create a rank 3 matrix that is in 4 by 3. So it's a 4 by 3 matrix with full column rank. So it's a rank 3 matrix. And then a vector, it's also in R4, all using random numbers generated from or drawn from a normal distribution. Okay, and then what I think you are going to find when you run this code is that this vector v it's possible that it's going to fit inside the column space of matrix A, but I think that's really unlikely. I think it's almost never going to happen, maybe sometimes. Okay, and then we generate a 4 by 4 matrix A and see whether the vector v in R4 is in the column space of this matrix A. And here I say I'm willing to bet 1 million Bitcoins, even more than that. I will bet a billion Bitcoin. Okay, there aren't a billion Bitcoins. I will bet 21 million Bitcoins that you will always find that vector v is in the column space of matrix A when A is a random matrix with that is 4 by 4. There's going to be no coding mistake. Okay, now I don't actually have 21 million Bitcoins or even 1 million Bitcoins. But I'm extremely confident that you will always get that this is true. Again, that is because we can assume that matrices drawn from random numbers have their maximum possible rank, which means that A, we can assume, is going to be a rank 4 matrix. So when we augment an additional vector onto that matrix, it's not possible for the rank to increase, which means that the column space of A already spans the entire 4-dimensional space, which means that any vector is, by definition, going to be in the column space. Okay, yeah, and then this last part here is just to put this code inside a Python function that returns true or false. Okay, so now let's switch to Python. Let's see if I have to come up with 21 million Bitcoins to pay you. So here is the function, the Python function that I created. It takes as input a matrix A and a vector V, and we compute the rank of A and the rank of AV, and AV is done by horizontally stacking A, so we have matrix A and then vector V at the end of it. Okay, and then we compute we determine whether those two ranks are the same. So if they are the same, this function will output true. If they're different, then it will output false. Okay, so then I can run this code. Here I have A to be a 4 by 3 matrix, and V is a 4 by 1 vector. And here we are getting false. So false means that the ranks of these two matrices are different, which means that this vector is not in the column space of matrix A. And we can run this over and over again. It's always going to be false. Maybe if you sit here for a couple hundred years, keep running it, you'll get true. Why is this almost, it's not guaranteed to be false, but it's very likely to be false. Why is it very likely, though not guaranteed, that a random vector V is not contained in the column space of matrix A when A is 4 by 3? To explain this, I'm going to go back to some of the code from chapter 3, and that was about creating this visualization of the span of a matrix with 2 columns. So you remember in this chapter is actually 2 vectors, but then in the previous chapter, we transform this into a matrix, or we conceptualize this as a matrix. So here we have a three-dimensional ambient space, and we have the column space of this matrix is defined by two vectors, and that creates a plane. Now, imagine that this is matrix A. Now, okay, in this exercise here, matrix A is 4 by 3, so we're working in a four-dimensional ambient space, and the matrix A is a three-dimensional subspace of that four-dimensional space. But, four dimensions are hard to visualize. So I'm just using this as a convenient tool for helping you understand the concept. So three-dimensional, in this visualization, three-dimensional ambient space, we have a two-dimensional subspace. Now, this plane, I'm only drawing some limited number of dots here, but it goes to infinity in all four of these directions, but it's this infinitely thin plane. Now, if we come up with some random vector, a three-dimensional random vector, and plot that vector in this three-dimensional ambient space, what is the probability that that vector happens to be in this plane, in this subspace? It's possible. It's just really, really unlikely, right? The vector could be here or here or here. It could be anywhere. Could even be, right here. It could be really, really, really close. A random vector could be really close to this subspace, but it's not going to be exactly in it, which would mean that the rank of the matrix, when we augment the matrix with the vector v, the rank is going to increase. So that's the visualization. If you really want to think about this in four dimensions in R4, the way that I like to think about R4 is taking the first three dimensions to be space and the fourth dimension to be time. So you can imagine a cube that's, sort of changing over time, and then the time is like the fourth dimension. So now imagine that the entire duration of the universe, from the Big Bang all the way up until the cold death of the universe, however the universe is going to end, it's a really, really long time. It's trillions of trillions of trillions of trillions of years. And now what this is telling us is that we have the infinite expanse, spatial expanse of the universe, but it only lasts for one instant, one infinitesimal fraction of a second across the entire duration of the universe. Now you pick a random time point in the universe, a random point in time and space. What is the probability that that random point, which is this vector v, happens to fall at exactly the instant where this matrix is existing? It's possible. It's just really, really unlikely. Okay, anyway, that is the solution and some explanation to this exercise. I hope you enjoyed it.